Now, when it comes to the ideal gas law, PV equals nRT, R equals, oopsies, 0.0821. I always like to write my units, liters, liters, atmospheres, mole, Kelvin. I like to write it out because then I know if whatever the problem I encounter, I have to bring it back to those units, those liters, atmospheres, moles, and Kelvin. Okay, so one of the kind of, I don't know if I'd say it's tricky, but one of the kind of fun problems that instructors usually like to throw at you, and I am one of those instructors, is I like to throw questions where you have to manipulate the ideal gas equation. So you have to take that PV equals nRT and figure something else out about it. So right here, what we've got is MM times PV divided or equals GRT. Okay, so MM, we've talked about that. MM is molar mass. Okay, now G, generally when we see the equation, it's PV equals nRT, but here we've got MM times PV equals GRT. Well, that G is mass of a gas. And we know that if we have, or we could say N, the number of moles, is equal to G divided by the molar mass. Because we know if we know the amount of it and we divide that by the molar mass, we're going to figure out how many moles of that gas that we actually have. So what this basically did, this equation right here, was it took that N value and kind of broke it into G and MM and distributed those two components. And it distributed them so that we have this MM times PV equals GRT. Okay, so what this sort of question can lead you to is a number of different pathways, but let's go ahead and continue on. One thing that this can do is if you have that, you could take molar mass times P times V equals GRT. You could take this D right here, density is equal to mass of a sample divided by the volume that it occupies. Okay, so you could be given a question where you have the molar mass of a substance, the pressure, the R value, and the T value, and be asked to figure out the density of that gas. So these are all kind of manipulations of that ideal gas equation. Well, defining these, MM is molar mass, P is your pressure in atmospheres, V is your volume in liters, G is grams of the substance, D is density of the gas in grams per liter, not in grams per milliliter. T is your temperature in Kelvin. Now, this is not, I don't know if I want to say it's easy, but this is something that's a little bit challenging, but you know how to do it. You know how to do this algebra. It's about keeping things straight, and so you can, relate values to one another. Like right here, this N, well, I know that N, number of moles, is equal to a mass divided by a molar mass. Well, I can just plug those things in to my ideal gas equation and end up with something that looks like this. PV equals G times MM times RT. Well, I can multiply by MM. That gets it off of this side, and I have to do it to the other side as well. So MM, and now all of a sudden I got that. So this is algebra. I'm not going to say it's easy, but I do know that you know how to do this. It takes practice though. The last variable was your R value, your ideal gas constant, 0.0821 liters, atmospheres, mole, Kelvin, divided by moles, Kelvin. Okay, now a good practice problem is this right here. Calculate the molar mass. Okay, that's what we're looking for. I'm going to highlight that. The molar mass of a gas, if 4.40 grams of the gas occupies 3.5 liters at 560 millimeters mercury and 41 degrees Celsius. Oh man, Dr. Gray, you are the worst. This gives you everything, but it gives you in units that you need to convert from. Okay, so PV and RT. I'm going to write my R value equals 0.0821 liters atmospheres divided by moles Kelvin. Okay. I'm given a volume, 3.5 liters. So I'm going to write that out. Okay, then I'm given a pressure in millimeters mercury. Okay, so I know that 1 atmosphere is equal to 760. Oh, 760 millimeters mercury. Okay, so if the pressure of my sample is 560 millimeters mercury, well, I know that I have less than 1 atmosphere, or the pressure is less than 1 atmosphere. I'm going to get my calculator out, and so I'm going to do 560 divided by 760. And whenever I do that, I figure out that the pressure is 0.737 atmospheres. Okay, so I've got my pressure, I've got my volume, my temperature. Well, this is in degrees Celsius. I need to convert that into Kelvin. So I'm just going to add 273.15, which gives me, let's see, 273 plus 41, 274, 314 Kelvin. Okay. Now the last thing, I need to figure out my molar mass. Well, I know that N is equal to grams of my substance divided by molar mass. So that's what I'm looking for. So I multiply each side by molar mass. Molar mass times N equals G, so I divide by N, and now I'm left with, I'm going to write it down here, molar mass is equal to grams divided by number of moles. Okay, I have my grams. What I need to do is I need to figure out my molar mass. Okay, now whenever I plug all of this in, okay, so I've got my R equals 0.0821. What I want to do is I want to go ahead and isolate. Okay, just a second. I'm sorry, folks. Bear with me. I made a mistake up here. I do not need to do that. What I need to do is I need to take my N equals, just a second, my N equals G divided by MM. I need to plug that in. PV equals G over MM, put that in parentheses, times RT. I'm going to multiply each side by molar mass. Cross that out, multiply this side by molar mass. Now, I've got MM times PV equals GRT. Okay. Now, do I have, let's see, what do I have? Do I have the pressure? Yes, I do. Do I have the volume? Yes, I do. Do I have the G, the amount of my gas? I do. It's 4.40. Do I have the R? Yes, I do. Do I have the temperature? Yes, I do. Okay, so divide each side by molar mass. Divide by molar mass. Okay, scribble, scribble, scribble. Now I'm left with an equation that reads P, oh, nope, stop. Okay, undo that. Sorry. Got ahead of myself. That's what I just did. What I need to do is I need to divide each side by pressure and volume. Okay, so PV. This gives me an equation in which molar mass is what I'm solving for. Molar mass is equal to GRT divided by PV. Plug all of these things in. And I get molar mass is equal to 4.40 times R 0.0821. My temperature is 314 Kelvin divided by my pressure is 0.737 and my volume is 3.50. Okay. And I get a gas with a molar mass is equal to about 43.97 grams per mole, or about 44 grams per mole. All right, I've done everything right. I kept all my units straight. This really wasn't too tough of a problem. It does take some time, but I assure you, it's all doable. All right, now when we go on from here, we've got something known as the combined gas law. The combined gas law relates pressure and volume of two different gases to the temperatures of those two different gases. So you can look at this almost as being similar to C1V1 equals C2V2. So the pressure of one gas times the volume of one gas is proportional to the temperature of that one gas, and that is ultimately equal to the pressure times the volume divided by that second gas's temperature. This is whenever the number of moles of that gas are kept constant. Okay, so ultimately what that gives you is a relationship between the pressure and temperature of two different gases when the moles are kept constant. Kinetic molecular theory is an idea in which gases consist of large number of molecules that are in continuous and random motion. So every single particle or every single molecule of a gas, they are constantly moving. The volume of those molecules of that gas is negligible compared to the total volume in which that gas is contained. So we already talked about that in terms of the space between atoms within a molecule of a gas. It's like 0.1%. So kinetic molecular theory kind of builds on that. The attractive and repulsive forces between gas molecules are negligible to one another. And energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. So if you change that temperature, the average kinetic energy of the molecules does change, okay? The average kinetic energy of the molecules is proportional to the absolute temperature. At any given temperature, the molecules of all gases have the same average kinetic energy. Now, this brings up the last thing, and that is, what is an ideal gas? An ideal gas is one in which all of the postulates of the kinetic molecular theory are followed. So in terms of energy transfer between different molecules and the space occupied by the molecules or the individual atoms of a gas. Under specific conditions, however, gases become less ideal. So that means they do not quite as, they do not follow that kinetic molecular theory quite as to the T. So pressure and temperature are both going to change. At high pressures, gases are less than ideal, or are less ideal. They behave less ideally. At low temperatures, gases are also less ideal. Okay, but more times than not, the problems that we're talking about will focus on that ideal gas law and that ideal gas equation. So if you understand that and how to manipulate that, you really have a good understanding of how gases behave, what volume they're going to occupy, how many moles of a gas are in a given sample. All right, well, next video is our last one for the semester. I hope this is helpful. Email me if you got any questions. Thank you very much. I'll see you later.